The vertical asymptotes will be x equals 7 and x equals negative 2. So for this function, the vertical asymptotes are 7 and negative 2. What are the zeros for this function? 5 and negative 3. Zeros come from the numerator, vertical asymptotes come from the denominator. We don't have any holes because nothing canceled out. Now here's the thing. This inequality for this problem is strictly less than. So do I want the zeros to be included as part of the solution? No, because they're equal to 0, and I only want output. I want to know what values of x would give us outputs that would be less than 0 or below the x-axis. So for these, when I do my sign chart, I'm going to put open circles because of the inequality. Okay? So when I do my sign chart, I'm going to do open circles. I do not want to include those in my solution set. But the vertical asymptotes, those don't have any points, right? They're not really above or below the x-axis. So I should also do open circles for those because they're never part of my solution set. Okay? So up here, something to be aware of, vertical asymptotes and holes are never part of the solution set. You're going, or sets, intervals, whatever. You're going to need to find them and put them on your sign chart, but when you give your final answer for, hey, these are the intervals of x that make that inequality true, you want to make sure that you have parentheses around them, not brackets, because they don't even exist. Whereas for the zeros, if it's less than or equal or greater than or equal, then I might fill those in with solid dots and include them in my solution set. So we're going to make a sign chart using these values. And so we've got negative 3 on the left. Negative 2 is the next number, then 5, and then 7. I don't do a number line. Technically, you're supposed to. I'm okay with you just doing a sign chart. I don't need it to be, evenly spaced and all that. But I do need, for everything to the left and right of each one of these critical things that are happening to x, we need to know whether it's positive or negative. So I've got to do this since I have 4 things on there, I've got to find 1, 2, 3, 4, 5 signs. And I'm going to put open circles at all of these because it didn't have equality and 2 of them are vertical asymptotes. So in my graphing calculator, since nothing canceled, instead of, if I'm going to put the function in like this, I'd have to put a big bracket around those and a big bracket around those. I'm just going to go back to my original function and put its numerator in parentheses and its denominator in parentheses. I go to my table, and now I'm going to test something to the left of negative 3, and it gives me a positive value. So on my sign chart, I put a positive so that I know that to the left of that 0, the graph is above the x-axis. Between negative 3 and negative 2, I'll do negative 2.5. You can do any decimal value between. That is negative. So that means that on the graph, that section of the graph is below the x-axis. Between negative 2 and 5, I'll pick 0. That's positive. And between 5 and 7, I'll pick 6. That's negative. We should expect to get alternating signs. When might I not get alternating signs? When there's a multiplicity of a root. So we saw that yesterday. You have to be really careful about that. They should not alternate. I still would suggest to you to still plug them in and double check. And you can expect signs to alternate, but double check it on the calculator. If I graph it, I should see exactly that. To the left of negative 3, the graph is above the y-axis. To the right, it's below. To the right of negative 2, it's above the x-axis. To the right of 5, it's below. To the right, and then to the right of 7, oh, I didn't do that. Whoops. Got to do an 8 because I have to go to the right of 7. It's positive again. So those are my intervals. And these are x values. 2 of them were zeros, 2 of them were vertical asymptotes. So the answer to this inequality, which is really saying, when is this function less than a height of 0 or an output of 0, When is the height below the x-axis? The answer is that it's below the x-axis between -3 and -2, but not including them because that would be on the x-axis. Well, for the -3 anyhow, the -2 has no value at all. And between 5 and 7, but not including either of those. Yes, sir. Yes. Then it won't matter. It should change signs for odd multiplicity. It's for even multiplicity we have to worry about. Because odd, it will cross the axis still. Yeah, but for the even multiplicity, it's going to bounce at that x-intercept, so it'll stay on the same side of the y or the x-axis. All right, looking at this next problem. Again, we need to factor the numerator. That's a good question. And the denominator. Are we going to have any holes? No. If we did have a hole, would we include them in our solution? No, they would just be a boundary. They wouldn't have equality with it. Now this one does ask, when is this function greater than or equal to 0? In effect, it's asking, when is the output, the height of the graph, above the x-axis? So we find the zeros first. That's easy. N equals -2 is the 0. Should I fill that in with a solid or open circle? Solid when I put it on my sign chart. And then my vertical asymptotes, which will not have equality, are n equals 0 and n equals 4. So on my sign chart, I have to put -2, 0, and 4. Again, I don't care about you evenly spacing them for the number line, but I do care about you having them in their relative place. The smaller number on the left, the larger number on the right, and increasing in order. So now I'm going to plug this original function, nothing canceled, so I'll go back to the original function. In parentheses, I have x squared plus 4x plus 4 divided by, in parentheses, x squared minus 4x. I go to my table, and I'm going to test values to the left of -2, a value between, between -2 and 0, a value between 0 and 4, and a value to the right of 4. So since I have 3 values on my sign chart, I have to have 4 numbers. So this is, well, I know why, but I'm thinking some of you might be wondering why these two are positive. Because it had even multiplicity, so it bounced. So when the graph was coming down, we're going to pretend this is a graph for a second instead of a sign chart. When the graph was coming down, it bounced back up. So those both sides stay above the x-axis. And then it did eventually, well, that was an asymptote, so it couldn't cross that. On the other side of the asymptote, it was negative. It was below the x-axis. And then over here, it was positive on the other side of that asymptote. And we can see that if we click the graph, it should match up, that up to -2 and even to the right of -2, it is above the x-axis. Once we hit 0, we see the graph jump down here. Then we see this vertical asymptote, and the graph jumps above up here. So that is the correct interval. We're answering for when it's greater than or equal to 0. So what should, oh wait, I didn't fill in my sign chart completely. This should have a solid dot. These should be open because they're the asymptotes. So I know when I'm writing my interval, I need to include that. If this were a minus sign, what would this interval be right here? Less than or equal to -2, but as a domain interval, an interval notation, it would be -∞ up to and including -2 with a bracket, right? But it's all plus signs, so does it really stop at -2? No, it keeps going all the way up to 0, but not including 0. So -∞ up to and not including 0. If that had been a minus sign, then I would have stopped it at -2, and it would have been a bracket to show equality. And then from 4 to infinity, and not including 4, though. So those are the intervals for which the graph is either on the x-axis or above the x-axis. Questions on that problem? All right, let's take a look then at, we're on 2.6 solving rational equations, or rational equations. Warning here that you can clear fractions only if you're solving an equation, not for the equality. So if you're like, oh, I'm going to try to solve this, like we solve rational functions, and you're turning it into a quadratic and getting answers for x, that's when you're solving it if it had an equal sign. This isn't an equal sign, it's an inequality. So we're actually graphing a rational function. We got to keep that denominator and find out what happens. There's two ways to do this. Now, you can either make this problem look like the ones we just did by coming up with a common denominator and converting this to a fraction and combining like terms. That's fine. But really, if you're just making a sign chart, what is it that you have to find? There's a couple things you got to find. What are they? Zeros and vertical asymptotes. Okay? So here, we have a vertical asymptote of -2. So we can't have equality with that. We need to find the zeros. I can go through all that work, or I could pretend it's equal to 0 to find the zeros. So I've got 3x plus 4 over x plus 2 minus 3 equals 0. Well, we just finished that skill with 2.5 a couple days ago, so what could I do to solve this equation? I could add 3 and then do what? Multiply by x plus 2, because it's the least common denominator. Some of you said, well, just add 3 and put it over 1 and cross multiply. It will have the same effect in this case since it's one ratio equals another. So if I multiply this by x plus 2, that factor cancels. I'm left with 3x plus 4. If I multiply this by x plus 2, I have 3x plus 6. So the least common denominator being x plus 2. That's what I get. Well, that means that 4 equals 6. There are no zeros. Can't always tell that looking at the graph, so you do need to set it equal to 0 and solve to see if there are any, and then you can check them on your calculator. But because sometimes the asymptote is so close, if I graph this, it's kind of hard to see, does it cross the x-axis or not? This way I know it does not. All right, so I don't have to worry about any zeros. I just have a vertical asymptote on my sign chart, and we can never have it equal to that because there is no output at the vertical asymptote. And so I'm going to put the function in my calculator. Quantity 3x plus 4 divided by the quantity x plus 2 minus 3. And then I go to my table and test a number to the left and test a number to the right. And I get to the left that it's above the x-axis. To the right it is below the x-axis. And so the answer to this inequality for which values of x is this function less than 0, the answer would be from, but not including, -2 to infinity. Questions on that problem? All right, for our last problem here, same idea, except when we're solving inequalities, what do we need to compare it to? 0. So I'm going to actually subtract 1 from both sides so that I can compare this to 0. So when I'm solving my inequality, I'm going to be considering this. That's what my sign chart compares it to. Now, in terms of solving for the zeros, I do want to leave it the way it was. X plus 5 over 2x minus 6 equals 1 helps me solve this. Multiplying by the least common denominator of 2x minus 6. On the right side, I get 2x minus 6. On the left side, I just have x plus 5. So now I get subtract x, add 6, get x equals 11. So on my sign chart, x equals 11. Should that have an open circle or a solid circle? Solid, because there is equality for this inequality. And then I also need to find the vertical asymptote. Anybody know what it is? X equals 3, because I would add 6 and divide by 2. So now I've got 3 on my sign chart, which should have an open circle, because there is no output for a vertical asymptote. And 11 on my sign chart, which I should have a solid dot, since we can have equality with 0, since it's greater than or equal to 0. In my graphing calculator, I enter the function x plus 5 divided by 2x minus 6 minus 1. And I could look at the graph, or I could look at the table. I put in 1, I put in 5, I put in 12, just numbers to each side of these numbers. I get a negative to the left of 3, positive outputs between 3 and 11, and negative outputs from 11 to the right. Since they want to know for which intervals this function is greater than or equal to 0, the answer is what? Who has an answer? 11, bracket around 11, because there's equality. Okay? I would like to go over the next examples, but I think we're going to have to try to sneak that in tomorrow, because a lot of you were not here yesterday for polynomial. It's the same thing for polynomial, except you don't have vertical asymptotes to worry about. But you have to factor or get those zeros from the graph, or use the rational root theorem to find them, or divide them out, or use the quadratic formula to find any irrational roots. So you might want to go back and look at that video if you were not here yesterday and haven't seen it yet. But we'll come back to this tomorrow. I know you have your quiz tomorrow on 252, so we took some time today just to have you do some practice for that. So we'll come back to these two problems. For now, hopefully you can say, yeah, I can solve rational inequalities. If you're unsure or the answer is no, then you need to come see me. The assignment for this section that's required for you to qualify for the reassessment policy are these problems, those odd problems. The review problems might help you, though, if you're looking for some more 2-5 practice to get ready for tomorrow's mini quiz. Okay. Our benchmark test is on Wednesday. But with Election Day being Tuesday, we don't have school Tuesday. So tomorrow you'll receive a quiz review. You'll have your mini quiz. You'll have not quiz review, a BA review tomorrow. And we'll go over questions from that on Monday. Jacob.
Is the homework due tomorrow or after?
The homework, okay, so tomorrow's not a normal quiz. You know how on our schedule we have the big quizzes, and you have to turn in all your assignments that led up to there to qualify. I'm not checking. I'll check everything in the day of the BA for the 2-5 and 2-6. And I'll have a sheet ready for you tomorrow. Yes, Cooper. I do. For the BA or for the mini quiz? For the mini quiz, go back to your 2-5 practice. If you guys want extra stuff, there should be some stuff in the online practice book, or come see me, I can get you something.